How we doing? All right. Surviving? You guys ready for the semester to be over? What's that? It is almost spring break. That's the right way to look at things. Good to see you back, Kevin. All right, this is good. I'm glad we have a fair amount. I think that hopefully this will not be our last class. So there's some inclement weather to be expected on Thursday. It's probably one of those little wintry mixtures, and so if this is our last class, then well, farewell. No, hopefully we will get a chance to put a bow on all of this at the end, but we are going to finish up the back half of the standard cosmology today. And then if, as long as we do get one more class on Thursday, we will wrap everything all together. I want to make sure everybody's on the same page about the final project. It is due on Saturday, right? This Saturday. I've had a few people email me about that. I assume everybody else is doing all right. I just want to clarify, for that project, you pick one object in the universe. You don't pick two different objects. So you pick one object, you're going to talk about its formation model under the different gaseous and liquid paradigms. You're not going to pick two different objects. Just want to make sure you guys understand that. Creativity projects, also get those in this weekend if you've done them. There's a couple of really cool ones already uploaded. So that's worth a lot of points if you want to do it, if you're worried about your grade in any way. I was just looking quickly over the grades this morning. Seems like everybody's either getting an A or failing. So it's on you guys. Get your work in, or you will probably not pass, and that is a huge waste of time and money for you. What else did I want to say about that? Questions about any of this business stuff? I'm also going to convert all of your missing quizzes to zeros this weekend, probably. I'll start doing it anyways. Same with the lab. If you haven't finished your labs up, you need to get those in. I don't believe there's a lab assignment the last week of class. There is, during finals week, one last 2-minute video assignment, but it shouldn't take very long. So do that as well. Questions, concerns? All right. So last week we talked a lot about redshifts and relativity, tried to address, kind of wind down some of this discussion of black holes. We got into dark matter, dark energy. Where are you guys at with that? Talk to me. I'm going to give out some attendance points here to wrap things up. By the way, remember guys, the attendance is also worth as much as anything else in this class. It's worth as much as your final. So probably too late to be explaining that to you, but talk to me. I want to hear from you guys. Yeah, Isabel.
We covered this specifically in class, but I covered it in my video last week. I saw someone's article about like planets being swallowed by suns. That was really interesting because I only thought like black holes.
Yeah, the sun is definitely gobbling up all sorts of stuff. It's interesting to think maybe we could have lost some planets in the past too. You know, we talked about very briefly in this course about how our solar system's pretty weird looking. It's missing some of the most common types of planets. So what happened to them? It's an interesting possibility. The sun's eating asteroids and comets all the time, actually. Pretty common. Jupiter's also eating a lot of comets. And so, yeah, that's a definite possibility for sure. What else? You guys think? Thoughts about redshifts and the first half of the Big Bang story?
Talking about Bogarts, and you said that it could reach up to like 95% the speed of light. I thought that was interesting. Is it possible that anything other than light could reach up to the speed of light, or is that just like?
No, yeah, it seems to be a speed limit on motion, and that seems to be empirically determined, but also falls out of the general relativity equations. Particularly, it's a postulate that goes into special relativity, which is a complement to general relativity. It is quite interesting. It seems like the speed of light is the fundamental limit on things. And I tried to give an example last time. I don't know if you remember this, but I was saying that actually waves that travel in any medium, whether it's the ocean or just a sound wave in the desk, they're all limited by really the material properties in which the wave is traveling. And light is a really weird situation because most physicists today don't consider light needing a medium to travel in. And I tried to at some point break down how that happened, that people kind of abandoned it. Does anybody remember why in the world people stopped looking for the medium of light and gravity? Yeah, they couldn't find it. So they postulated, they sort of imagined, they assumed that the medium would be separate from the atoms themselves. And so there would be a little bit of a lag as the Earth was moving, the light would kind of miss, if you reflected off a mirror, basically it would miss the location because the Earth is moving, right? And that didn't seem to be the case. So they kind of threw up their hands and gave up on it. And it's very strange how sometimes in science, when these things happen, people don't revisit those ideas and they just move on. The other answer is that it didn't matter, in the sense of they were able to develop all sorts of wonderful technological devices, spacecraft, radios, all of this. It didn't seem to really impact things, whether there was a genuine understanding of the medium of light and gravity. All that you needed was the equations that described how the light unfolded, how gravity unfolded. And that's kind of the funny difference between technology and science, ultimately. Is technology is all about making things work. You get equations that you refine in your experimental apparatus until you understand exactly how your variables relate to each other. How does gravity depend on mass? You can do experiments to figure that out. Same with light. But at the end of the day, science isn't necessarily so concerned with building stuff. The science really comes down to how do things work. And so it's easy to get the two confused, science and technology. Most people kind of think of them as one thing. And of course, technology can use scientific ideas to build cool stuff, but it doesn't necessarily need to. It can often just tinker around and experiment and parameterize. So yeah, people moved away from it, yeah.
Talked about the redshifted areas and how it potentially could be that over the time that it takes for the light to get us, that some of the energy has just been kind of dispersed, so it just appears red, but actually is just normal. And I was also really curious about the blue shifted areas and why they're moving differently.
Yeah, it is very interesting, especially most of these big redshifts come from these distant galaxies and from these quasars that we were talking about. And of course, the explanation that the quasars could be moving at 96% speed of light is a bit preposterous, because moving a galaxy with that much mass at a speed that's even, close to the speed of light is unimaginable. So that led to the interpretation, essentially, that the space itself was expanding, that these weren't actual recession Doppler velocities, that somehow the space expanding explained those massive redshifts. Which is weird. It's a kind of a circular argument, because you ask what space is, and space is really just the distance between objects. And so it's like, okay, so you're saying the distance increased, but it's not a recession velocity. I don't know. It's just a very strange argument. And what we're going to look at today, because the Big Bang hypothesis that all of these things are rushing away from this initial moment of the universe, it's largely dependent on that redshift relationship that we talked about. It's also dependent on this thing called the CMB, and which we'll do today. And what's really interesting is that most of the people that were studying this redshift business originally didn't resort to a Big Bang model. They actually assumed that the redshift was due to some sort of loss of energy, whether it was due to the ether or whatever the medium was that was absorbing some of that energy, or interactions with interstellar materials along the way. Almost all of the predictions about what would cause that were not due to anything like the Big Bang. And so the conversion of that idea into being a Big Bang narrative was very abrupt, and there was a lot of dissent about that prior to the discovery of this CMB thing that we're going to get into today. So it's a very interesting situation where we're, our entire model for the universe at the moment in the consensus science, let's say, of the mainstream astrophysicists is based on this Big Bang cosmology, but it's really resting on two main lines of evidence, one of which is this redshift, which, as we pointed out, there seems to be many possibilities for what could cause a redshift at a great distance. And the other one is the CMB, and I think we're going to see today that there's also many possibilities for what could be causing that have nothing to do with the Big Bang. And so that will hopefully make sense. As far as the blue shifted ones, Mia, it's very interesting, you know. The idea is just that, well, perhaps on a local a local spatial scale, so like nearby galaxies like Andromeda might be blue shifted because they're rushing towards us, but the ones that are far away are the ones that we consider in the cosmological model. Only those really distant galaxies that are super red or those really distant quasars are the ones that we point to when formulating this idea of expansion. So yeah, very, very strange little anomalies. Plus, not to mention the strange business of quasars we talked about too. We talked about one of Hubble's graduate students, this guy named Halton Arp, who noted that there was, you know, what he believed continuous structures between these quasars and nearby galaxies, and he didn't buy that the quasars were as distant as the cosmological expansionists thought that they were. So that's really interesting too. What else, Michael?
I guess, because I wasn't here last time, but as far as like the Big Bang, I guess that's why I've always been interested in the Big Bounce theory versus that, because it doesn't put like a finite timeline, even if all of the Big Bang theory is correct. It's also, I guess I think about it, who's to say that the Big Bang or bounce is happening in one central location? And that's like another reason you could explain things moving closer and things moving further, because they didn't have the same origin.
So there was another group, that's a really good point. So Michael's talking about, well, couldn't there just be like multiples of these points upon which everything is receding from? And he links it to this big bounce idea, which I think I'll deal with next time. But it's interesting because if you start reading about the debate, particularly in after the 1960s when the CMB was discovered, there's a whole camp that is arguing for a steady state universe that gets a lot of attention. And this was headed up by Fred Hoyle, who was another British astronomer. But what's interesting is that there's a bunch of other alternatives that aren't really discussed in those mainstream Wikipedia pages. The interesting thing about Hoyle's camp is that they too assumed that the redshift referred to a recession velocity. And so they were arguing just what you're saying, that it's possible the galaxies are moving away from us. They're all moving away from each other because there's new galaxies forming in between them, essentially, and they'll push the old galaxies away. And so it looks like everything's kind of moving away from everything all the time. But it's really just a cyclic cosmos where there's new galaxies being formed, old ones are falling apart. And this has been going on forever, basically. I think one of the reasons that is held up as a punching bag a little bit is because they too assume that the redshift distance relationship is a recession velocity. And so the question becomes, what if it's not a recession velocity? What if the that's almost never given a lot of attention, because if it's not a recession velocity, then the only thing you're really left with is this CMB. And I think we'll see, at least, I will make the case to that the CMB, even being cosmic in origin, is a very shaky proposition. So I'll make that case for you guys today as well. So yeah, I mean, this is all, by the way, happening. This whole discussion is happening in the face of some really shocking discoveries from the James Webb Telescope, which is our next generation telescope. It's kind of the replacement for the Hubble. Where I showed you some pictures last time. You missed this one last class, Michael, but I was showing they basically found these galaxies. They thought, we'll look back to the beginning of the universe with this new powerful telescope, and we'll see these primordial galaxies being formed for the first time. And instead of finding primordial galaxies being formed, they found fully formed galaxies, which contradicted, the entire plan of the Big Bang, essentially. And so it seems like that story is going to change no matter what. The question becomes, does it change into, well, there's still a Big Bang, it just happened earlier than we thought, or does it change into something that isn't Big Bang oriented at all? And that has yet to be determined, but something's going to change. But what else? Yeah.
Like realist and positive.
Nice.
And like the cosmological principle of like physics must work the same everywhere. It all must be the same as what we're experiencing here on Earth.
Yeah, that's an interesting piece of the whole puzzle. Do you remember the positivism versus the realism at all?
Things like, oh, you have to have something there, like, it has to have an explanation.
Yep.
Or like, it doesn't matter.
Yeah, the positivists are more, they're more like, well, there's a limit to human intellect. Like there's things that happen that we can't possibly comprehend. And I want to be clear, that's not the same as saying there's things we can't observe because we're not technologically adept enough to observe them. They're literally saying that your brain is not powerful enough to comprehend parts of nature, which I find a really disempowering philosophy. But it does seem to be the popular philosophy in the modern physics community. It justifies things like, enormous densities in zero volume, or, unobservable materials that account for 96% of the universe, stuff like that. So that has been very popular. It really triumphed in this debate between Einstein and Bohr, which is very famous. It's often said that Bohr won this debate because he was essentially arguing between the wave versus particle. The argument was between the wave versus particle nature of reality. And of course, quantum mechanics says that things can be both particles and waves at the same time. Einstein was very dissatisfied with that. He found it was a very unreal interpretation of the statistical mechanics of quantum mechanics. But Einstein didn't know how to explain it. He didn't have a material explanation for this wave behavior, this strange, the double slit experiment, stuff like this, where it seems like the photon goes through both slits simultaneously. How do you explain that? He didn't know. And so it's an interesting situation because people will say that Einstein lost that debate. But if you read the actual records of the people who were at the conference, the Solvay conference, it seems like Bohr and his colleagues, Heisenberg, et cetera, these people were very unhappy they couldn't convince Einstein to come over to their camp at the end of the day. So it was a little bit of a Pyrrhic victory. Nobody really won. But that seems to be the world that we inhabit right now, is that quantum mechanicists in general say that these things that don't make sense, it's okay they don't make sense because the universe is incomprehensible fundamentally. And so that's just the trend that we're at right now. I personally hope that doesn't continue into the future, but it is where we're at, these things. It's a really good point. What else? Yeah, sorry.
Question: if there is, instead of a black hole, a central star graveyard in the center of our galaxy, what would be the mechanisms by which cold, dead stars would end up there, but living, burning stars wouldn't get into the mixture? How could that occur?
Yeah. Well, there's two possibilities that don't involve the black hole. One could just be enormous stars themselves, because what we see empirically when we look at the center of the galaxy is really bright stuff. It's really, really bright, especially these active galactic nuclei, where it's just unbelievably powerful, luminous stuff coming out of it. So one possibility is that there's just megastars there. But in either case, I think that the mechanism wouldn't be so dissimilar from a solar system, that things gravitate towards the center because that's where most of the material is, something like that. So it's treated as a gravitational system, and things are just sort of yanked into it. And perhaps they combine or collide, but something super energetic is happening there. So yeah, some possibilities. I mean, you could also imagine that the dead stuff is outside of the arms of the galaxy and the kind of halo around the galaxy as well, which people have tried to use that to explain the dark matter business, right? The rotation of the galaxy that doesn't quite make sense. And usually the arguments against that are that, well, if there's big heavy stuff out there, it should be the light coming past it from distant stars should be gravitationally lensed. But I made a case to you about gravitational lensing in general, where I said I'm not entirely convinced that gravitational lensing is a thing, in that we don't usually observe it in situations where we should. Right? There's a lot of galaxies and stars that are in line where you should have lensing that you don't have lensing. And even in our own solar system, we only see lensing within the plasma boundary of the sun's atmosphere. And so if gravitational lensing isn't a thing, I don't think that we would be able to see cold stuff anywhere, because it doesn't radiate. It doesn't even have infrared heat because it's cold. So there might be a huge graveyard out in the kind of halo around our galaxy too, that we just wouldn't have access to. So that's an interesting piece of the puzzle as well. It's quite interesting, like, given that all these things I'm telling you, you might be wondering, like, why in the world people haven't started investigating new ideas, or there aren't multiple competing ideas right now that are being discussed in your textbook and so forth. And, I think there's something really interesting and almost mythological that happens when humanity as a whole has to change its mind about these things. So, I always like to point your textbook, by the way, if you're, I don't think, Levin was here last semester, but one of the chapters of your textbook earlier on from last semester deals with the Copernican revolution. And it loves to herald the Copernican revolution as this triumph of science where reason wins out. So the Copernican revolution was obviously when all of a sudden people went from thinking that the Earth was at the center of the solar system to the sun being at the center of the solar system. And it is true that it was this triumph of reason and everything. And it had been, a millennium of people in the academy, whatever semblance of the academy existed in medieval Europe. But there had been 1,000 years of people with the wrong model. And the wrong model worked really well. It made accurate predictions, but it was wrong nonetheless. And so people like to talk about how Copernicus was this revolutionary who envisioned things differently, and everybody changed their mind. It's not quite that simple, as the thing. The truth of the matter is that Copernicus was terrified of the way that he was starting to see the model as being different than the way that everybody and all the leading scholars were thinking about it. And he actually wrote his piece quite early in life. He had a book that he wrote about the changing worldview. And he carried that book around, this is the legend anyways, that he carried it in his breast pocket for his entire life. I think he obviously wasn't a professional scientist. I think he worked in medicine and politics and a bunch of different things. And it wasn't until the end of his life, when he was about to die, that the printing press had just become a popular mode. And he actually self-published his book by himself right when he was about to die. And he handed it off to his best friends, essentially. And the same thing happened with Charles Darwin, too. He's also one of these heroes of science. Everybody thinks, wow, Darwin had this awesome idea, and everybody loved him for it. Darwin was terrified of what people would make of his ideas, actually. And he also had been writing this enormous book his whole life. And he was also planning on essentially saving this thing until he was basically about to die to publish it, right? And the only reason he published it earlier than that was because he got wind that there was another guy named Wallace who had basically come up with the same idea of evolution as him. And so he got together with Wallace, and they actually kind of agreed to publish together. So again, it's very, very, very difficult for people to risk everything to come out and argue against these massive narratives, especially if most people who control the superstructures of discourse, the journals and the academies and everything, if they're all working under one paradigm, you sound a little bit loony if you try to imagine something completely opposed to that, especially if you're not an astronomer, right? Now, it's worth mentioning again, Copernicus wasn't an astronomer. He wasn't in any way associated with the professional academic world. Darwin also, same thing. He was essentially a naturalist. He was not, he went to seminary school, right? His degree was essentially in religious studies. He was not part of the professional cool kids who were making theories about the geologic history of the Earth and the biologic history of the Earth. The funny thing is that usually when revolutions happen in science, they come from people outside of the discipline, because people inside the discipline become really accustomed to the stories that they grew up with and that they learned from all their professors and everything like that, right? So it's a strange lesson that we never seem to learn in science, that we get married to these ideas, they begin to fall apart, often for several decades, maybe hundreds, sometimes in the case of the Copernican revolution for thousands of years, or 1,000 years, before somebody actually changes everybody's mind all of a sudden. And of course, Copernicus died. He was not known for his ideas when he lived, Galileo eventually picked up on some of those ideas and made a scene that got him in a lot of trouble. He died under house arrest, right? Really pissed off the Pope at the time for advocating for Copernicus's ideas. So it's a very dangerous, professionally, not physically, but professionally dangerous thing to advocate for something that flies in the face of a very popular idea. And I think we're very much in the same situation today. This liquid sun model that I've been kind of talking about with you guys is a very interesting piece. It's a very interesting paradigm that I think is changing under our feet right now. The person who's done the most work on that, this guy named Pierre Marie, I had you guys watch one of his videos on Sky Scholar on YouTube. Pierre was professionally a radiologist. He worked on MRI machines and so forth. He was not an astrophysicist by training. And that's basically excluded him from the dialogue. It's been very painful for him because people inside of the astrophysics community only want to hear from other astrophysicists who have the same pedigree as them, which is quite tragic. Somebody in my Discord server the other day pointed me to a paper that came out of Washington University in St. Louis, a very big research university, by an astronomer who had essentially argued for the liquid sun for the first time. And it's really tragic because she didn't cite Pierre's work in any of her writings. And, I guess she could make the case that she didn't know about Pierre, but anybody who Googles the liquid sun would find Pierre very quickly. Now, I don't necessarily fault her for it, though, either, because, again, when you're inside of these institutions, when you're a professional astronomer, you have to cite other astronomers, you have to cite other astrophysicists. That's kind of the politics of the game. It's a very strange situation. So the sort of tragedy of it is that, perhaps this paradigm will shift in the next few years towards a more liquid model of stellar physics. I think it's unavoidable that will happen soon. But it might not result in Pierre getting any credit for that for many, many years because he's not part of that crew. And so there's something very interesting and almost sociological about the way that these paradigms bust open and change over time. It can be quite tragic for the people who are doing them. Again, Copernicus, probably the most famous revolutionary in all of science. No credit whatsoever while he was alive for his work. Very strange situation. And of course, credit is all we have as scientists. We're not paid for thinking that much, right? You don't get millions and millions of dollars for coming up with a cool theory. You get your name in the history books. And so it's really quite a tragic situation oftentimes with these revolutions. All right. So there is another, let's move past seeing red. There's an argument, there are various arguments about the elemental abundances, how much of each of the atoms exists in the universe based on either the Big Bang or otherwise. I'm not gonna have time to get into those, but I do wanna focus on the second big leg of the Big Bang today, which is this cosmic microwave background business. Let me make sure that I've finished saying everything that I wanted to say about the redshift first, though. One thing I do think is worth reiterating is that what's gone on with the Big Bang is not an illogical process. This is really important for you guys to understand that logic is essentially a series of if-then statements by which you process assumptions or evidence that go into an argument. And what we're going to see, and what we've seen hopefully so far, is that along the way, people have had assumptions that went into them believing that this redshift, for instance, is the result of an expanding universe. That's a logical deduction if you assume that something like space can expand in the first place. If that's part of your assumption set, then perhaps it is a logical conclusion that the explanation for the redshift is the result of expansion. If you assume that doesn't make any sense and that space is just a metric for measuring distances and that it cannot be treated as a substance itself, then you can't make that logical conclusion. So it's not necessarily a matter all the time of people being illogical when theories go bankrupt and you get a new paradigm all of a sudden. So, okay. So the basic idea, of course, was that given those recession velocities, if you traced those velocities all the way back to a given point, in other words, if you fit a curve to those recession velocities based on the redshift, that you could arrive at a date for the beginning of the universe. And this time upon which all of this took place is generally referred to as Hubble time. Now, it's an interesting proposal on its face that if you know the position and the motion of a bunch of particles, that you could rededuce what the starting place looked like. I wonder if you guys are comfortable with that on its face. You know, this might be a reasonable idea for certain projects, right? But let's say I took an aquarium that was airtight and I put an ice cube in it and we filmed it. And over time, the ice cube melted and eventually all the water molecules were into gas. Some of them were melted on the floor. Would it be reasonable to take a movie of the end points of that experiment and then be able to somehow look at that movie and reconstruct an ice cube from it? Could you do that? You probably couldn't do that. What if I used a mold and I shaped it like a dinosaur first, and then I did the experiment? Would you be able to run the movie back based on the last few seconds of the experiment and deduce that I had an ice cube shaped like a dinosaur in the first place? It's kind of a really strange proposal, but that's essentially what we're doing with this redshift reconstruction of the universe back to this very homogeneous isotropic points at the beginning of the universe with the Big Bang model. So, you know, I understand, again, it's really logical to want to do that. And it's logical to see these recession velocities and say, well, if we trace them back, the logical moment would be this point of infinite density where everything occurred. But it's a little bit like trying to reconstruct the dinosaur-shaped ice cube from a puddle of water at the end of an experiment when you only have the last 2 seconds of a 10-hour video. All right. Make sure that we have time for the CMB here. All right. So another conclusion from basically this redshift business was where the whole Big Bang business, the whole Big Bang idea came about, right? From being able to retrace these velocities back to an initial points. Now, people started thinking, and this, I believe, is a picture from your textbook of the way that the universe was expected to have cooled over time as a result of this Big Bang. So it's often the story that's told, and I believe the story that's told in your textbook is that, you know, people predicted that after the Big Bang, well, first of all, that in the moment of the Big Bang and in the subsequent few seconds, it would have been a really hot, ultra-dense substance that was it was too hot for atoms to even exist. It was just this sea of God knows what. And that essentially, just like if you let the gas out of a spray can or something, it gets very cold over time. There was a cooling process, and that cooling could somehow be predicted and mapped onto this story with the recession velocities, that you could have this predictable cooling possible. And so the kind of simplified story that your textbook gives us is that people imagined that the cooling would have a predictable rate to it, and that people believed we should be able to measure the temperature of the backgrounds of the universe as a result of this cooling process. And that what actually happened was that those predictions were made, and then, you know, in early 1960s, people discovered that they could actually see that glow of the early day of the universe, and that the predicted temperature of that glow was identical to the predictions that were lodged ahead of time. That is actually not how it happened at all. It's actually quite a different story. The reality of the situation is that people who were making predictions about the background glow of the universe were actually trying to interpret the way that all of that, how they were basically trying to explain that redshift in non-expansion models. So most of the people who were working on that project were trying to imagine how the universe would be heated up in order to dissipate the energy such that we would observe these really high redshifts at a distance. So they were, in a sense, trying to prove the background temperature of the universe would be the result of the cooling due to that light that's actually traveling from enormous distances. They all had embraced something of a steady state or an eternal universe. And none of those people, with the exception of a couple that I'll talk about in a minute, thought that it would be that this glow should have anything to do with the birth of the universe itself. There was only a couple of people that ended up doing that. So, again, this is all very logical. A very dense material as it expands should cool. This is a process that we know to be the case. The question of whether that's what we're observing is also on the table, and we'll get to that in a second. So let's talk about the main narrative for this Big Bang. Basic idea was that in the very beginning, and this is so biblical sounding, but in the very beginning, there was only light, right? There was no matter, there was no particles, there was just light. It was too hot for anything else to exist. And so, I'm just fast forward. Basic idea is that, after some very small fraction of a second, you essentially have just light combining, you get the production of some initial particles eventually. It takes some time, on the order of thousands of years, for you to actually form atoms, right? Now, this is all well and good, but again, I take a little bit of caution with the idea that we can have light without atoms. That's an assumption, right? That's an assumption that you can have light without atoms. No one's ever observed light without atoms. In fact, I think I pointed out to you guys that the very famous chemist G.N. Lewis, who did a lot of the work with how electron bonding happens in chemistry, he was one of the first people who stood up on his chair and said, hey, guys, why are we talking about light like it's these little magic things that are thrown off of atoms? It's clearly a transaction that's happening between one atom and the next. There's always an emitter and there's always an absorber. Light seems to be some sort of interaction between atoms. It doesn't seem to be this magic, bowling ball of energy that's cast off into the darkness. And so right away, that strikes me as a very strange assumption at the heart of this Big Bang cosmology. But the basic idea is that there's all of this light swimming around. Eventually, these atoms are able to constitute themselves as the whole mess cools down. And when the atoms form for the first time, they absorb a lot of this light. They don't absorb all of it, though. Some of the light just continues off into interstellar space. And so this background temperature of the universe is measured from light. And the prediction being that, or this isn't even a prediction, the explanation for that background light, which we call the CMB, is that it is the escaped leftover light from this beginning moment. It's the light that wasn't eaten up by the atoms at the beginning of the universe. Now, the thing that's really disturbing about this, if you've been paying attention at all about the black body radiation discussion in this class, is that light, which we call the CMB, is in the form of a black body, right? So if you've been paying attention at all, you're probably aware that black bodies in the laboratory on Earth, in every experiment that's ever been done, can only be produced by solid or liquid bodies, right? They're never, ever produced by gases. What's really strange is that the explanation that's given for this black body spectrum that we see with our telescopes here on Earth, and with, we'll get into the observations of the CMB in a second, it's supposed to come from this moment at the beginning of the universe when there were no bodies, there were no atoms at all, there was nothing. It was just this leftover sea of photons that for some reason happens to be a black body. Now, the nice thing about it being a black body, if you're trying to defend the Big Bang, is that black bodies allow you to calculate a temperature. And so they could quickly convert this light into a temperature, which they could assign to this sort of heat story that we talked about, the cooling of the universe, right? Again, if black bodies can only be made by solids and liquids, then this entire story goes with it. And we'll take a look at what else could possibly be causing that as we move forward. Now, a lot of people, prior to the discovery of this cosmic microwave background radiation, had made predictions about, like I said, about the background temperature of the universe. And what's really interesting is that most of those predictions were based on a very different idea. They were largely based on sopping up of that energy by the interstellar medium, and some of them hinted at it as being the results of all of the stars left, the cooling of stars, the background glow of the stars once they kind of reached thermal equilibrium with one another. Now, that's a really interesting proposal as well, because we know that stars have beautiful blackbody spectra. And even if we leave aside the liquid versus gas debate, assigning this perfect cosmic microwave blackbody spectrum to stars on its face makes a lot of sense. So there was, if we look at the history of this debate, of these predictions about the CMB, it's really quite interesting. So one of the first people to ever make this prediction was this guy named Regener. This was in 1933. He predicted a temperature of about 50 Kelvin on the blackbody curve. So of course you get, remember on blackbody spectra, the way the peak shifts gives you the temperature. People came along, Alpha and Herman predicted about 5 Kelvin. They were also working under the Big Bang model. There was a huge proponent, one of the biggest proponents of the Big Bang was this guy named Gamow. And Gamow actually kept increasing his temperature all the way up to the discovery of the CMB. So he originally suggested around 7K based on his mathematics, using the Big Bang trajectory that we talked about with the redshifts. By 1961, Gamow was predicting 50K for the cosmic microwave background radiation. This was just 3 years before it was discovered. And of course, the final temperature that was discovered for this background black body was 2.7 Kelvin. So that's a really interesting situation, right? Where you have one of the biggest advocates for the Big Bang model who had made a prediction about the temperature of it, which was actually an order of magnitude off from what it turned out to be. And it's a very strange situation that the textbook would write it, that these people had predicted, based on the Big Bang, they had predicted that the temperature would be 2.7, because the truth is actually couldn't be further from the case. Actually, the people who had nailed it in terms of the 2.7 had assumed something like the background stars at thermal equilibrium had produced the 2.7. This was many, many years beforehand. So, story goes that these two, let's say, engineers, essentially, who were working at AT&T's Bell Laboratories in Homedale, New Jersey, were sort of tinkering with one of their radio receivers, and they noted this strange black body hiss in the microwave range during one of their experiments. And they published this, and very quickly, actually in the same journal issue, another group came along and said, well, that background hiss is clearly a fingerprint of the Big Bang, which is very strange. I'm not aware of too many places in history where somebody makes an observation, publishes it, and in the same journal, it's decided what the cause of it was, based on some rather enormous debates that was happening at the time, which was Big Bang versus steady state universe. But it was assigned immediately to the Big Bang. And of course, all of these earlier papers were sort of reinterpreted to seem like they had been predicting that it would be 2.73 Kelvin all along the way. And like I said, that just wasn't the case. Almost all of these people, from Eddington to Regener, and many of these people had made predictions in the early days about what the background temperature would be. Those people that were correct, they had actually not used anything, they had not embraced the Big Bang cosmology to make those predictions, which is very strange. Now, let's talk about this microwave background stuff a little bit. It's actually quite interesting. So the strangest piece of the microwave background, and here's a picture of it as measured on Earth. The strangest thing about the microwave background is that it is a perfect black body. So I have a picture of the solar spectrum over here. The yellow curve is what a perfect black body looks like. And you can see that the sun, the actual sun, it does have a black body-like shape to it. There's divots taken out, of course, because gas in the atmosphere is absorbing and so forth. But there's a lot of noise on the solar spectrum too. When you try to measure the black body spectrum of the sun, it's kind of a jagged curve, right? It's not this perfect black body. I mean, the only way you can get a black body that's this perfect is in a laboratory, essentially, by heating up a soot-covered chamber, essentially, by putting something hot inside of it, allowing them to come to thermal equilibrium. So this is really weird, because generally speaking, when we point a telescope at the sky, there's a lot of noise involved. I showed you guys, we talked about that black hole picture and how much noise actually went into the image that was generated and eventually stripped away through a bunch of image processing and so forth. But the reality is that whenever we look up at the sky, whenever we make measurements in science in general, they tend to be extremely noisy unless they're in really controlled laboratory conditions. But this cosmic microwave background radiation was perfect. There was almost no noise to it at all, which is really, really weird, actually, if you think about it. It means that this signal was really, really strong, actually, right? It means that it was super clear and it could not be confused with anything else. And so, what's been interesting over the years is that, well, okay, we picked up this black body signal here on Earth. Okay, that's kind of interesting. So the next logical thing to do would be to send up weather balloons and try to measure it. They do that. It's also really, really, really clean, a beautiful, noiseless signal that they get on these weather balloons. The next thing they do is they build this satellite to go into low Earth orbit. It's called the COBE satellite. And the COBE satellite also looks for this signal and it finds it. It's beautiful. There's almost there's no error bars on it whatsoever. It's just a beautiful, beautiful signal. Very, very strange. And you would think that the next thing that you would do is then take a spacecraft and go far away from the Earth and try to measure it. You would think that's what you would do. And everybody thought that's what they should do. So what they did was they launched two more satellites. One was called the WMAP and one was called the Planck satellite. And they actually situated these things way off at the Lagrange points that we talked about. So they were kind of balanced on the other side of the Earth-Moon system, right, at L2. And instead of actually trying to measure the CMB directly, they did something kind of sketchy. With the WMAP satellite, what they did was they said, well, we know what the temperature of this signal is. So what we're going to do is we're going to assume that it's 2.7 Kelvin, and we're going to take a radio antenna and we're going to point it both directions in the sky. And we're going to just subtract the values at 2.7 Kelvin for a black body from either side of the sky. So we're basically going to make a differential map of the microwave signal in either direction. And that, of course, gives us this beautiful picture that everybody is so familiar with. Of course, not without a great deal of image processing, which we'll deal with in a second. But the point is that when they went to L2 for the first time, they didn't actually measure the CMB. They didn't measure what we call the monopole of the CMB, which is its actual, direct measurements. Why? I have no idea, but they didn't. And then the second satellite they sent out to L2, which is called Planck, they did something even more dastardly. They actually took a source with them that was that they had warmed up to 2.7 Kelvin, and they compared the signals that they saw with this signal and measured, again, the anisotropy, right? The difference between their probe and the signal that they saw in the background, and they generate this heat map as a result of it. Now, what's really, why I say the Planck satellite's even sketchier is that the reference probe that was warmed to 2.7 Kelvin, it was actually in contact conductively with the heat shield of the satellite. So, of course, according to black body science, you can't have the system be in thermal equilibrium with another structure and measure the temperature of it. So it's highly likely that they didn't even have a black body system in the first place from which to compare it. But at the end of the day, it was still a differential map where they compared the probe versus whatever they saw in the background. So what's interesting about all of this, and why I even waste time telling it to you, is that we've only actually ever measured the CMB here on Earth. And the tightest, most beautiful recordings we've got of the CMB were the ones that were here on Earth. Not only were they here on Earth, but they were in Homedale, New Jersey, which is very close to a giant black body emitter, which we'll talk about in just a second. The subsequent ones that were taken at the Balloon and eventually at Kobe were not as nice as the ones that were taken at that Homedale, New Jersey site, although they were very, very nice. And we've never gone ahead and done it at any distance from Earth, which is very, very strange. So we claim that it's a cosmic signal, but it's only really ever been measured here on Earth, which should give you pause for concern, especially if you realize exactly how beautiful that black body signal is that we get here on Earth. You know, again, those anisotropy maps that show the warm and cool pockets that are used either differentially or compared to an onboard probe, the first thing they got to do is subtract the really loud microwave signal of the galaxy, right? So they remove all of this foreground from the plane of the galaxy, because the galaxy is full of stars. They're great microwave emitters. So they have to delete all of that to even get the signal that you see in the anisotropy map. They also have to delete the Doppler motions of the Earth as it's flying through the cosmos, right? Because our Earth is moving really, really fast, something like 30,000 kilometers per second. It's moving really, really fast in its orbit, right? So that results in a Doppler blur as well. So they have to remove that as well. So again, a tremendous amount of image processing before you can even start to examine the heat map of the microwave backgrounds using these L2 probes. So I already told you guys about that. Again, this is the L2 point that I was talking about. This is where we plop those satellites, because they're stable gravitational wells, essentially, where you can have a satellite that will follow us around the solar system. So that's really interesting. So the best recordings of the CMB are actually from Earth. And these ones that are made away from Earth at L2, which is the furthest we've ever tried to measure it, they're not actual direct measurements of the CMB. They're really differential measurements that compare what we believe to be the temperature, and then we look for comparisons to that temperature, which is really interesting. So they take all of that data from Kobe, which was that low Earth orbit satellite, and they use that as their reference going into these. Now, my friend Pierre actually stumbled upon something really interesting, which is that communication satellites, right? So we have all these satellites that are going around making sure our cell phones work and stuff, right? Communication satellites will actually calibrate their position based on the CMB. This is something that everybody does because it's a known strong signal that everybody can use to calibrate the orientation. But what's really, really bizarre is that when they calibrate their satellites based on the CMB, where do you think that they point the satellite? This is very, very interesting. You would think that if they were measuring something cosmic, they would point the satellites at the cosmos, right? They point the satellite at the limb of the Earth, actually. So they point it at the edge of the horizon of the Earth in order to calibrate CMB. That's really, really weird. So here's some quotes from these technical journals where they talk about calibrating the communication satellites based on the CMB. So they're actually pointing at the limb of the Earth to find the peak signal of the CMB. That's really, really weird, right? Okay. Now, what's going on with that? So again, this is what they're doing. They're aiming for the edge of the Earth when they calibrate to the strongest signal of the CMB. This is really, really weird. Okay. Now, what could be going on? So if this signal isn't cosmic in origin, what in the heck could it be? Now, one of the most obvious candidates might be the Earth itself. In particular, the Earth. What is most of the Earth? It's water, it turns out. Now, water is an extremely strong emitter and absorber of microwave radiation. You guys probably have noticed this when you go to cook some ramen noodles late at night, right? You gotta add the water to it before the microwave works on the noodles, right? Water and microwaves love each other. In fact, if you go back to this original Homedale, New Jersey experiment where they first discovered the CMB, these guys, and you read their original logs, they're freaking out because water is getting into their horn antenna and it's messing up all of their calculations. So they're really, really worried about water. They are on the shore of New Jersey, though, right next to the Atlantic Ocean. So, the next question would be, well, could it be water, actually, that they're measuring as this cosmic microwave background source and not actually anything cosmic at all? And of course, the answer that's often given is, well, that's weird because we know the oceans are actually at a temperature in the 280 Kelvin range, right? They wouldn't be measuring a 2.7 Kelvin temperature of the oceans. That makes no sense. That would be near freezing, near absolute zero almost. It's really, really cold signal. So that makes no sense. However, there's another piece of this puzzle which is really fascinating. So radio antennas are really susceptible to the axis in which they're pointed at a signal. So there's a sort of phase relationship, and this is true for microphones as well. There's a polarization for a microphone, and you can put the microphone into different polarization patterns. So depending on how I decide to lens the light or to detect the light that's coming into a telescope, and the same goes for a sound device as well. I can either look at all of the waves that are coming in, I can look at just the waves that are in front of the microphone, and I can switch the polarity pattern on this microphone to do that. I can put it in a figure-8 mode, so it hears right behind, right in front, but nothing on the side. I can do an omni mode, where I listen to everything all at once, or I can phase cancel the back so that I only get the front of the microphone. Radio telescope construction is very much the same. You get very different signals depending on the orientation of the horn of the antenna. Now, what's really, really interesting is that if you look at the microwave signal and the way that these antennae are constructed, depending on the angle at which the source of that radiation is spread in the field of view, you measure a very different temperature. So what we're looking at here is actually the brightness temperature of water in these 3 different radio bands. And these are relevant to the CMB. These are different radio bands that are examined to construct that blackbody temperature. And what you see is that as you move from looking straight overhead at the temperature of a water source in the microwave region, a blackbody temperature of a water source, what happens is that as that signal moves off axis, so it moves away from the nadir, by the time that it's down to 90 degrees or so, away from the nadir, from the direct line of the horn of the antenna, the temperature falls off very precipitously to the point that you're almost at 0 degrees brightness temperature by the time that you're at 90 degrees. So if there's a source leaking into the horn from 90 degrees off axis, in other words, when they aim those satellites at the limb of the Earth, the ocean is exactly at 90 degrees to where they're aiming those telescopes. And sure enough, when you calculate the temperature that you should expect from the ocean as a result of the microwave signal at that 90-degree angle to the horn of the telescope, you end up with something very close to the 2.7 Kelvin that's reported. So this is really, really, really interesting. We have a situation where we have measured a microwave signal. Of course, when they were at that laboratory at Homedale, New Jersey, and they discovered this thing, well, the satellites were pointed up at the sky. The 90-degree angle was pointed right at the ocean at the time. The communication satellites also have that 90-degree angle where they calibrate their CMB. And all of the direct measurements of the CMB have happened here on Earth, not anywhere else. So it's a very strange proposition that this temperature would have anything to do with anything cosmic at this point, as far as I can tell. So there's another piece of this puzzle too, which is like water is not just water is not just a convenient black body in this system. So if you guys will recall back when we were talking about the sun, we were talking about what sort of lattice the sun might have in order to give us that perfect black body. Well, in the laboratory, when we make black bodies, we use carbon-covered chambers, right? The soot-covered chamber. The lattice in a soot-covered chamber is this perfect hexagonal planar structure, right? We talked about the difference between soot and diamond is just a matter of the lattice. the diamond has a more cubic looking structure to its lattice. The soot is this perfect layered hexagon structure. What's really interesting is that water in its nascent form, it does the exact same thing. So water also forms a hexagonal lattice, very similar to soot, especially under pressure. So it's a little bit puckered in a different way. It's not exactly the same, but it should ideally make a fantastic black body source. Now, this is a really interesting case of that, where during these tests that were done with the nuclear bombs, you guys maybe have seen some of these where they blow up all these ships in the middle of the ocean. One thing you might not have noticed is when these bombs were going off, there's a little ring that travels along the water as it expands out. And that ring is black. It's completely black, actually. And so when people were trying to explain what was happening in the water, what they deduced was that what had happened was the water had been shock compressed such that the lattice actually was more flattened, so that the water actually had this kind of planar structure to it. Its hexagonal lattice had been flattened in such a way that its optical properties changed. It changed in such a way that it became opaque to the visible radiation. Light couldn't penetrate the water all of a sudden because it had taken on a more perfect black body character than otherwise. So water essentially has all of the wonderful properties that we would expect from a perfect black body, especially under compression, which it certainly is at the depths of the ocean. So again, if you absorb a radiation, just like water, you have to also emit that radiation. This is Kirchhoff's law. This is this fundamental law of black body science. If you absorb a particular wavelength, you must also emit that wavelength. We know water is a fantastic absorber of microwave radiation. All of your guys' late night cooking projects prove this. We should also expect that water would be an enormous emitter of microwave signals as well, particularly in the black body spectrum. So, all of this to say that perhaps this CMB business is an echo of the Big Bang, but perhaps it's something a lot more mundane. Perhaps it's something much more close to Earth. And then the question becomes, well, how bizarre is it? Because we've already given guys Nobel Prizes for discovering the birth of the universe through the microwave background signal. The people who published that journal article right after the observation in the same issue, they got the Nobel Prize for that discovery of the birth of the universe. So that's a huge monument to climb over. You know, we were talking about Copernicus and Darwin and these people who were terrified of upsetting the apple cart. Well, how much worse is it now that we have Nobel Prizes given for things that may not actually turn out to be true? How bizarre is that? I don't think we've ever had to deal with such a situation where somebody's gotten a Nobel Prize for something that turned out to not really be appropriate in its interpretive scope. That's a real monster to climb over. So I think overturning that paradigm, is going to be not an easy task for whoever comes next about it. Although I think that it is possible. I think it will probably take some time. I think the people who actually got that Nobel Prize for the CMB are still alive. At least one of them is still alive, to my knowledge. And they're very old. So perhaps they will expire and people will not have so much hesitance about moving on with ideas. But yeah, I don't know how you overturn a paradigm as long as the Nobel Prize winners are still alive. It just seems like too large of an embarrassment. I don't know. What do you guys think? What kind of thoughts do we have? Michael?
I think you'd have to just handle it with, I guess, the mindset of take it as, I appreciate your work. I'm gonna use that as a stepping stone and expound on what, like, the path you were on. So, like, we're now moving into more, we have better equipment, we have better ways to measure things. I think that's the way to approach it without, like, blowing up the whole community.
I think I love to think that it could be like that. I think it's true, first of all, that, like, look, science is a process of making mistakes, of learning new ways to see things, right? I think there might be a lesson involved in that about, hey, maybe we should chill out for like a few issues of the journal before we decide what this signal means, right? That's one of the things that's very bizarre about this, is that the guys announced the discovery of this strange radio signal, and the next, I literally think it's the next paper in the journal is the Nobel Prize winner saying, hey, that's the echo of the Big Bang. And everybody's like, yeah, great, it is. I wonder if there's a cautionary tale about, hey, let's chill on that idea for a little bit before we announce it as being the case. But yeah, I don't know. I think we have to be super forgiving as the scientific community about ideas that fail. I think we have to, it's very hard to detach yourself from your ideas as a scientist, because that's all you have, right? Like I said, we're not getting millions of dollars for coming up with cool ideas. We only get reputational, brownie points, basically. And so there's a lot of esteem and reputation and ego tied up in these things. So yeah, it's a very, very interesting situation. What do you guys think? Anybody? Right, yeah.
know how much a satellite that would actually measure it would cost, or how one would go about getting a grant or getting that started.
I know. Yeah. I had a really funny conversation with ChatGPT before class today about this exact question. I was like, I was like, why haven't we tried to directly measure the CMB at L2? I mean, isn't that kind of weird? And ChatGPT literally responded, I should pull it up. It's a really funny response. This is worth the wait, I think. Sorry, it's worth it. It's worth it, I promise. All right, I asked it, why don't they actually go and do a direct measurement of the monopole at L2? ChatGPT says, good question. Here's the no bullshit answer. 1, Kobe already nailed it. So they already did it in low Earth orbit. 2, it's hard to do better than the measurement that they did in low Earth orbit, the Kobe Firas satellite. 3, focus has shifted. So people are interested in new stuff. They don't care anymore. They think they've already nailed it. And 4 is cost versus gain. It would cost money and they think they've already nailed it, so they don't need to. So that's a really, really interesting situation. And I think that one of the things that's kind of obscured in that answer is that most people have no idea that heat map that everybody shows you of the CMB isn't a direct measurement of the CMB. So even a lot of people who are working in the popular science communication world and so forth, they're all under the impression that we actually measured the CMB at L2. They think we have measured it away from Earth, but we haven't. And so I think it's a combination of people think we already did it versus we already nailed it in low Earth orbit, so who cares? It's just a very, very strange constellation of bizarre pieces. And I think whoever's teaching this class 100 years from now will be telling a really interesting kind of fatherly lesson of how things can go sideways when we're how we have blind spots in science and all of this stuff. I think it's going to be a great chapter in the history of science eventually. And I think we'll learn how to do science better as a result of it. I think that we'll learn from these mistakes and so forth. But we are absolutely living through a remarkable paradigm shift with respect to all these things. And they're really going to change the way that we see this project in the future. Any other thoughts? Yes, Levin.
So are you saying that the water is spinning at 280 Kelvin, and then because of the way it's aimed, it's big enough as microwaves?
Yeah, exactly. It has to do with the polarization angle of the signal.
Like, what does the water, like the water loving microwaves? Like, what does that have to do with it if it's not emitting at microwaves?
Oh, it emits at microwaves that even if you point it. So if you take a satellite and point it directly at the ocean, you would measure about 280 Kelvin. If you moved it off axis, you would measure the ocean at around 2.7 Kelvin, which is the background radiation. Sorry?
With the higher wavelengths being filtered out?
Well, in the microwave, they are long wavelengths to begin with, right?
Well, I mean, like sort of,
Like the optical wavelengths and stuff like that. So water doesn't normally have optical black body.
I mean, like. Does it get shifted to the microwaves? Because like.
It's not shifted. It has a microwave black body spectrum to begin
Yeah,
with.
like what happens to the other wavelength?
Let's understand why when we look at it from one angle, the spectrum is different versus the other. Like, why do you get the microwave signal when you're looking off axis?
Well, you get the microwave signal either way. Yeah, that's what I'm trying to say. So you can get a microwave black body temperature of the ocean if you point it directly at it, but it will be a different temperature than if you look off axis. Basically, the temperature changes. The peak of the spectrum shifts depending on the angle of the horn of the antenna. Essentially, does it make sense?
I actually don't know.
I mean, it's a matter of phase cancellation of signals. Like I don't know how to give that explanation non-mathematically right now. It is an empirically defined thing. I don't know that I can try to come back on Thursday and explain to you why that peak shifts towards the cooler.
The question about like why it's different off axis.
No, it's just. Like if the water has 280 Kelvin, it's mainly like infrared. Like,
It's microwave still. It's not that you can measure that signal still at the same frequency band, right? It's just that the temperature is going to shift depending on where you point the satellite, essentially. You point it at the source, you'll measure the accurate temperature of the ocean that we understand.
it's 280 Kelvin microwaves.
Yes, it would still be a microwave. It would still be a microwave signal, yeah. Anybody else? Yeah. Hi.
If the telescopes are pointing just away from the Earth, what's the temperature it's picking up? Like that's actually pointing at, or is it not picking up any temperature the way it's facing? Only picking up the 2.7 from the water.
So, like the Kobe Firas satellite?
Like when the satellites are calibrating based off of supposedly the microwave background, are they not picking up the temperature the way they're facing and only picking it up from the 90-degree angle?
That's right, yeah.
So then wouldn't that mean that there isn't any temperature like outside of the Earth that they're
Yeah,
atmosphere?
it's problematic, yeah. Yeah, because what they're doing is they're looking for that signal. They're finding the strongest point of that signal and they're using that to calibrate essentially where their altitude is, because they find that at the limb of the Earth. They use that to essentially as a surrogate marker for their location, their altitude. Basically, they triangulate based off of it. So they go out and they're kind of moving their horn around looking for the strongest CMB signal, which they find when their satellite is pointed directly at the limb of the Earth, which puts the ocean directly at 90 degrees to them. It's very strange stuff, guys. It's very, very strange stuff. Yeah. Good.
A CMB signal when you point in other directions that they can test?
I don't know that that's been done so far. It's very, very tricky to do these measurements on Earth in general. To do radio telescope projects, they're often done. Okay, so there is one. So it's very difficult to do measurements with radio astronomy on Earth, right? Because water is such a huge. The atmosphere in general is a real nightmare. So they often put them on top of mountains in the desert. We find a lot of these in like Chile in the mountains where it's very dry. There was actually an Armenian telescope that was built when Armenia was part of the Soviet Union. And they went to great lengths to put this thing way out on a mountain in the desert. It's called Haruni's antenna. It's essentially a bowl that's shaded on all sides from everything around it. And what's really strange is that the Armenian astronomer Haruni, who reported when they first got this thing online, he actually wrote a paper where he said, I can't find the CMB all of a sudden. We have no measurement of the CMB. There's no CMB in my telescope. What's going on? It's a very, very strange piece of literature that was, of course, part of the Soviet system at the time. And still still stands, and unfortunately that telescope's fallen into disarray. I believe it's his daughter maybe, or his granddaughter is an astronomer who's trying to get it back online. So it'll be interesting if that telescope does come back into existence and they can actually show that it indeed does not show the CMB. Very, very weird stuff. Any other thoughts, guys? All right, so Redshift, CMB, those are our two pillars. Assuming we have class and we don't get snowed out on Thursday, we will try to put a bow on this whole project and look at what comes next, really, in terms of cosmology and astrophysics. But otherwise, yeah, it's been fun, guys. And I wish you the best of luck with your finals and everything. And I'll see you on Thursday, hopefully.